All right, welcome everyone. Thank you for coming so early. My name is Nick, and I am going to talk about data visualization. Just before we start, a few words about my employer. I work for a company called Fidzai, and we work with Scala, and we help to make the world a better place by preventing fraud in financial transactions. Think machine learning, big data, low latency. If any of that sounds interesting to you, just talk to me after this. We have offices in Portugal, in Porto and Lisbon and Coimbra, and in other countries as well. Right, so with that out of the way, this is what I call a reproducible live demo talk. And basically there are no slides. This is not a slide. This is a part of the demo. Another thing, there is a website where you can find all the materials for the talk. They should be actually enough for you to present this talk on your own, but I wish people wouldn't go around and present my talks all the time. And finally, if you have any questions, I would rather prefer if you ask them along the way and not hold on to them until the end, because it's very hard for me to backtrack to what I was saying before. So just shout and I'll try to remember to copy your question to the microphone. All right? So let's talk about data visualization. So I'm going to present this project of mine, a personal project that I've been working for a while, and it's called Reftree, and it allows you to create visualizations like this. Oh, okay. By the way, this is the link if you want to see the materials. Anyway, this project gives you a very simple API, and you can produce diagrams like this with very little effort. How little? I think we are going to find out. So here, I apologize for the small resolution. Here we have an Ammonite session, a Scala console, and a simple image viewer, which is going to display all the images that we render. So a very simple setup. And let's start with something like, say, a case class person, classic example. Well, this is going to be fun. Yes. And now we have someone called Bob, which is a person with the name Bob and age 42. And we can render that person. So that's it. There is no setup, no configuration. You just render to a file that you want. Currently, it just renders to the same file so that the image viewer can pick that up. And that's it. And it's fairly configurable. You can import some implicits. And for example, if you want to show this as name and not first name, we got that covered. So that's it. This can be used for different purposes. So in the previous talk, we had an example of immutable data. And I actually find this quite handy for exploring immutable data. So if we have something like a list of some numbers, 1, 2, 3, we can render that list. And it has support for a few standard data structures like list, queues, vectors, and all of that stuff. And imagine we want to add an element to the head of this list. So we say list 1 is 0 prepended to list. Now, if we render both the list and list 1, we get something like this. So you can see that the new cell was prepended actually to the list, and the rest of the list was reused. Yeah, this is one of the beautiful properties of this type of data structures. Unfortunately, if you try to append an element to the list, you will find that actually you have to copy the entire thing, which is not really that good. So here you can see that we generate an entirely new list in green. Another data structure that we can take a look at is a queue. So fairly simple to construct again. Oh, sorry, that's the wrong queue. Yeah, so a queue actually has two lists, one from the front part of the queue and one for the back part of the queue. And you can add to the front in constant time, and you can add to the back in constant time. The only problem is when you start to remove elements, but we'll get there. So let's say we want to show q and q plus 4. So you can see here that now we can reuse the same front part of the queue, but we added a new element to the back list. And I think here Reftree really helps to understand what is going on. So this would be one use case. I find that it also helps to document your projects. If they're doing anything data structure related or algorithm related, you can use it to generate those visuals for the documentation. Or you can use it to give talks about Reftree itself, which is what I'm doing. Anyway, one feature that I particularly like is called animations. And if we wanted to understand a bit better what is going on with this queue if we try to add elements and then remove elements, this animation shows what is going on. And last year I was presenting this material about data structures and lenses and zippers and different kinds of functional programming techniques. And I realized that Reftree actually uses all those techniques to produce the visualizations. So I thought, why not talk about Reftree and the techniques used to visualize these techniques? Or to paraphrase Pimp My Ride. Yo dog, heard you like functional programming techniques, so I used functional programming to visualize visualizing functional programming. So looking at this visualization, I thought maybe it would be interesting to explore how to make this type of smooth animations, and how do we go about it, and how can we use functional programming to do this. So this is what we are going to discuss today. But before that, obviously we need to get a better understanding of how Reftree actually works. So remember our friend Bob? Render Bob. So how does Reftree come up with this sort of visualization for Bob? Well, the first step is to convert Bob to a generic representation, and I use Shapeless for that. Some of you might have heard about it, and I think it was presented yesterday. So it creates a data structure like this, which is a heterogeneous list that has the value Bob, the value 42, and that's with a heterogeneous, it's a terrible word to pronounce. Anyway, here in the type information, you can also see that Shapeless embeds the field names for us. So in this case, first name and age. So if we render this, it's just a simple list with a string that contains the name and an indent contains an age. So having that, we can obtain a tree-like data structure, actually a tree data structure that I called Reftree. You might be seeing where this is coming from. So Reftree of Bob is something like this. And we can actually use a Reftree of a Reftree to render the Reftree of Bob. So it's a fairly boring data structure that has lots of different fields and stuff. And I don't really want to get into detail here. But the key point here is that using this tree data structure, we can create a graph representation. So it would be something like this, graph of Bob. And we can actually encode this graph in a format called dot. And this format is understood by a tool called Graphies, which is able to generate images. So this is a fairly simple pipeline where we go from data to pictures of data. And one of the formats that I think will be useful for us is SVG. Is anyone here familiar with SVG? Who's familiar with SVG? Some people, okay. So SVG is basically a bunch of XML that is scalable vector graphics. That's what it stands for. And I think right now we are kind of understanding how we can go about animations if we have this SVG. Just we just make an SVG for every single frame, and then we just render them to some raster format and put them in an animated GIF, and that's it, right? Well, not really, because if we just did that, the animation would be really jumpy. Because remember, if we render Q, let's say 1, 2, and then we want to render Q 1, 2, 3. So if it was a part of animation, it would just jump like that, and it would be really hard to see what is happening. So what we really want is to do smooth transitions between the animation frames, or between the keyframes. And there is actually, I mean, it's SVG, right? So it's vector. We can just go there and we can tweak all the numbers, and that's it, right? We just need to basically move the nodes, morph the graph edges. We need to interpolate the colors, the transparency, I guess other things. So actually it's not that simple. And what I thought would be cool is if we had some sort of principled functional programming approach to this, right? Because if we just go there and start modifying things, it's very hard to track what is happening. So with that in mind, the abstraction that I came up with, it's called interpolation. And interpolation of A is something that, given two values, left and right, and a point in time between them, can produce an interpolation between those two values, right? And of course, if you can put a point in time, you can just sample the range between A and B, so you can have as many interpolation frames as you want. So that seems helpful. And to see how it works, I suggest that we start with the simplest thing possible, which is just a lowly number. It could be like an x coordinate of some node or something like that. So let's say we render interpolation double. And we sample the range from 0 to 10 with 5 points. So it gives us a list like this. Actually, I think now that we understand that lists are sequences of concells, I'm just going to simplify that. So import this. So I'll just show lists in this array-like visualization. Anyway, so we got what we wanted. So it's sampling of numbers from 0 to 10 with 5 points. Not really that impressive, right? So the next stage, we can interpolate a two-dimensional point. So a point is something like this. Let's say 10, 20. So this point has two coordinates, x and y. And if we want to interpolate from one point to another, we need to interpolate both, right? We can just go there and interpolate them, but it's kind of awkward. So in a great tradition of functional programming, what we are going to do is we are going to introduce more abstraction. And the right abstraction for this is that of a lens, or more generally, optics. So lens is something that gives you access into a part of a data structure. So let's say you have something of type A and something of type B inside. And lens gives you read and write access to that part. So let's create a few lenses and see how they work. Let's say X. So here I'm using the Monaco library, which is very cool. It can generate lenses automatically. So we have one for X and one for Y. So if we focus that lens on our point, we would see that it points, no pun intended, to the first coordinate, right? And in the same way, if we focus the second one, it points to the second coordinate. Everything is as expected. Now, what can we do with these lenses? One thing that you can do is you can get the data that it points to. So in this case, we get the x coordinate. You can set the coordinate to something else. So it gives us a new point with the data inside it modified. And we can modify it with a function, whatever was there plus 15. So that gives us a point of 25 and 20. So if you think about it, we have right access to parts of the point, which basically means that we can go there and interpolate each part separately and then combine those interpolations, and we would have an interpolation of a point, right? So it would be something like this. Points, we take x and we interpolate it with interpolation. I wish I called it something shorter. Plus y interpolate with interpolation dot double. So now that we have this interpolation for points, we can actually sample points. So render points sample, let's say point 1020 to point 2030. And we want 4 points in our sample. Great. So we have some pretty points here. So what is the next step? I would say the next step is polylines. Polylines are sequences of points, right? So if we have a polyline, like this one, it just has 2 points, 0, 10, and 10, 20. And if we have polylines of the same length or same number of points, we can just interpolate all the points individually, right? And again, we can use a bit of optics here. So we can say polylines is, first we obtain a length from polyline to the points that it has. And then we interpolate each of them with the point interpolation that we just created. So great, now we can interpolate polylines. So I can render polylines sample from polyline 1 to polyline 2. Let's say 4. At least. Well, it doesn't fit on the screen, but you can trust me that there are 4 polylines now. Well, this is great, but I think at this point you wish we did something actually useful. So I suggest that we do an interpolation of a graph edge. And the result is going to look something like this. So we had an edge that was in the graph, and in one frame it was here, in another frame it was here, or the other way around for you. And we just want to smoothly interpolate from one frame to another. Well, to do that, we need to understand how graph edges are represented in SVG. And SVG being XML, we can just look at it. So I have an example of an edge here, just a bunch of XML as usual. I can render it. So this has the root SVG element with some properties that we don't really care about. And then it has this path element, and that path element has a D attribute, which is just a string of nonsense. That we'll get to it later. So the first thing that we want to do is, if we want to interpolate this edge, we need to somehow get to the essence of it, right? To the actual edge definition. So the first step is to get to this path element right here. And I implemented a few optics that help us do that. So we can create a path, which is optics collect first. So here I have sort of poor man's SVG implementation, which has a poor man's CSS selector type of thingy. So we can select the path element. Oops, it's select, not selector. Right, so if we render the optic focus of path and our edge, you can see that it focuses on this path element, right? Now, how do we get to this attribute that actually contains the path definition? Well, the great property of optics, and this one is called an optional because there might be a path element or not, is that optics can be composed. So if you have an optic from A to B and an optic from B to C, we can compose them into an optic from A to C, just like we saw in the previous talk. So this is a great example of composition. So if we had an optic that focuses on attribute of XML element, we would just compose it with this one and we would get to the D attribute. So this is exactly what we're going to attempt here. Compose optional XML SVG API attribute of D. So if we render our optic again, well, this was supposed to be highlighted, but never mind. So it focuses on this part. Now, this part is still a bunch of nonsense, and what we really want is to get some sort of sensible case class that actually lets us understand what is happening in that path. And we can achieve that by composing with yet another optic, which is called an isomorphism. So if we have an isomorphism from string to our nice case class, we can just compose with that. And this would be path string iso. So path is a class that I wrote that is just a simple representation of an SVG path. So now if we do a path get option of edge 1, now we are finally able to see what is going on here. So we have several segments in this path. The first one is a move to segment that moves to a point with these coordinates. And then we have a Bezier curve going on with some control points and some target point. And actually here you can see very easily that the second segment starts where the first segment left off. Right. And the final piece of this is that if we have Bezier curves or any combination of different segments, we can actually approximate it with a polyline, right? We can sample it with a number of points, and we already know how to interpolate polylines. So that seems like a useful step forward. So we take our path and we compose with another optic, which is path polyline iso. And this one actually takes an argument, which is the number of points that we want. So I'm going to add it here. Right, so now we can do render path of, let's say, 3 points, get option of edge 1. Right, so we approximated our edge with 3 points, and if we wanted, we could approximate it with 5 points or any number of points. And let's think what we did here. So we went all the way from bottom to top, from a single number to a point, to a polyline, and we have an interpolation of a polyline, and now we went from top to bottom, from an SVG to a path inside SVG, to the attribute of that path, to the actual value of that attribute, which is a path, and then we approximate it with a polyline. So now we can combine these two parts together, and we get an interpolation for a graph edge. And it would look something like this. So def edges, again, let's leave the configure amount of points, is path of those points, I said point, is path of those points, interpolate with polylines, right? And finally, we can take this for a ride. So let's say render frames from edge 1 to edge 2, and we want to do edges with, let's say, 4 points, and we want 4 interpolation frames. So we get this very impressive interpolation here. Not completely happy with that, so I think we can bump that to 20 points and 20 interpolation frames. So this is more close to something that we wanted. And I think we can turn it up to 11 with 100 points, 100 frames. Takes a bit of time to render, but it's worth it. It's really smooth. So an interested reader could extend this approach to animate the transitions of graph nodes, colors, transparency, and all of those attributes or you can just go to the code base and see how I did it, which is actually fairly readable. So if you go here to interpolation, so there is a fade out, there is a fade in, there is an interpolation of color, interpolation of line thickness, interpolation of node position, edge position, nodes, sets of nodes or sets of edges, and finally there is an interpolation of SVG. Now this is the curious part. See, here it says SVG. What is SVG? We don't know. It's anything that supports this API. And what is that API? This API is just a bunch of lenses that tell us how to access different attributes. So let's say we want to have an optional from SVG to polyline. We want to have an optional from SVG to a path, and for text nodes, we want to have an optional from SVG to a point, which is the coordinate of the text node. What is SVG? We don't care. As long as we implement all those optics, we can operate on anything, right? And this is actually a great thing. First of all, because we never touch XML directly, which I'm sure many people would be happy about. And another thing is that you can support different implementations of SVG, which is exactly what I did. So since a week ago or so, Reftree actually supports Scala.js. So I have these implementations for Scala XML and for JS DOM. And it runs in JS just the same. And actually the parts that differ between Scala and Scala.js, it's like 50 lines of code each. So fairly generic. I think that speaks a lot about the great properties of lenses and functional abstraction in general. We abstracted over something. We used a lot of composition. And we got something that is very flexible and that is very easy to work with. And we didn't lose our sanity animating SVG. So one curious thing about this is that earlier on we saw this optic that was called collect first, and it focuses on an element inside SVG which is somewhere in there, right? And it's actually interesting how would you go about implementing something like that. Turns out this optic doesn't just support XML, it actually supports any sort of recursive data structure, so any tree, and you can implement an optic that focuses on an element of that tree. So to implement this, we are going to, again, introduce more abstraction or more functional programming tools. And the tool that is very useful for working with recursive data structures was introduced in a paper from 1997, and it's called a zipper. What's a zipper? A zipper is something that gives you kind of a cursor inside a recursive data structure, and you can go back and forth and focus on different elements, and you can update them. And of course, everything is completely immutable, so every operation that you do on a zipper just gives you a new zipper. So let's see how that works. I actually implemented a small zipper library that is very easy to use out of the box. So imagine we have some XML, simple XML. So it has a tree, has some leaves with some values, and has a subtree. Now imagine that we create a zipper like this, zipper of simple XML. Let's take a look at it. So simple XML and zipper. Right, so this zipper right now is kind of nothing special. You can see that it focuses on the root node of the tree. And this zipper has a few fields that are, most of them are empty. So it has left siblings, which is a list of left siblings of the current node. Right siblings, which is the list of the right siblings of the current node. And top, which is a pointer to the previous zipper. And we'll see how that works in a bit. So let's say we render this plus zipper move down left. So it's supposed to move to one of those nodes here. This one, I think. Right. Well, this is a fair amount of visual noise, but stay with me just for a moment. So this is our new zipper. that we moved down left. And you can see that in the top field, it points to the previous zipper, which will be handy later when we want to return to it. And as I promised, it focuses on this leaf node of the tree. So I think we can elide most of this information from here, because it's very hard to follow what is going on. Right, so it just focuses on this, and we can do various operations with it. We can say, for example, cycle, try, move right, and it will move right until it can, or until it can't, actually. So now we move to the subtree. We can do various operations like insert left or insert right, and it's easy to see how that works, because here we have left siblings, which is the list of the nodes that were to the left of the current one, right siblings, which is currently empty. So if we want to insert something on the left, we just put it on this list. If we want to put something on the right, we put it on this list. If we want to replace the focus, we just replace the focus. If we want to delete the focus and move to the left, we can do that as well. So this data structure provides a very easy implementation for moving around and modifying things. Now, the interesting thing is, imagine we went down this node. So move down left again. So now we are just in that small subtree that we had with 2 leaves. And let's say we want to add an element here. So let's say insert left, some sort of fruit. So now we have this fruit here in the left siblings. And now the interesting part is what happens if you move up. Well, this is actually what gave name to the zipper, because as you move up, you take all the elements on the current level and you zip them back together, right? So this new node that we added, it will be zipped with the nodes that already existed, and we just move to the parent zipper and we update the node that we were editing. So we say move up. And now we have the same tree that we had, but with a fruit. So this is actually a cool gardening tip. Anyway, you can also do another operation that is called commit, which is basically moving up all the way up the tree and committing all the operations that we did. So now we are just back to the original tree that has a fruit. And if you think about this, this tool that allows us to navigate around recursive data structures such as XML is a perfect tool to implement some of the optics that we used. So if you want to collect the first element, you just traverse the tree and you fetch it. If you want to update it, you traverse it again and you swap it with a new element. And that's actually it. I think this is all I have for you. Hopefully this was enjoyable, and thanks a lot. Actually, I lied. There is one more thing that I'll put running. This is implementation. This is an animation of a zipper at work with some numeric trees. So we have the zipper on the left and the tree on the right. And with the highlight, you see that they focus on the same thing. And now you know that to implement this visualization, we actually used zippers. So that kind of makes it very meta. Thank you. Questions? Yes?
Can this handle cyclic data structures?
Sorry?
Can this handle cyclic data structures?
So that's a good point. Currently, it's geared towards immutable data structures. I think you can get cycles with laziness. This is actually some of the next steps that I want to make, because I want to extend this with the type diagram tool. And for types, you're much more likely to get cycles. So I need to start handling those. And I'll just probably put some lazy stuff there and some cycle detection logic. But yeah, that's a good point. Currently, no cycles. Yes?
Hi. First of all, congratulations. Awesome talk.
Thank you.
Really good example of how functional programming principles can lead to very awesome design. So that was really cool. I have a question though. Can we use this tool for any arbitrary data structures? Like, I want to visualize my free program, a free monad. Is that possible? Like, I want to see how.
It depends on the of your dedication, I suppose. So what we saw in the beginning was the auto-derived visualizations, right, using shapeless. You can actually implement the type class that is called toReftree, as long as you can implement it for your data structure, and it just uses two types of nodes, refs, which are like any refs, right, objects that are pointed to by reference, or vals, which are like any vals. As long
Thank you.
So round of applause. Thank you, Nick.